4.7 Bond enthalpies. Delta CH is the enthalpy change of combustion. If you plot delta CH against the number of carbon atoms in the molecule for straight chain alkanes, you get a straight line graph. For methane with one carbon, delta CH is the enthalpy change for CH4 plus 2O2 equals CO2 plus 2H2O. The straight line means that delta CH changes by the same amount for each extra carbon atom in the chain. So each alkane differs from the previous one by one CH2 group. That is, there is one extra CC bond in the molecule and two extra CH bonds. This suggests that you can assign a definite amount of energy to a particular bond. This is called the bond enthalpy. You have to put in energy to break a covalent bond. This is an endothermic change. The bond dissociation enthalpy is then defined as the enthalpy change required to break a covalent bond with all species in their gaseous state. The same amount of energy is given out when the bond is formed. This is an exothermic change. However, the same bond, for example CH, may have slightly different bond enthalpies in different molecules, but you usually use the average value. This value is called the mean bond enthalpy, often called the bond energy. The fact that you can get out the same amount of energy when you make a bond as you put in to break it is an example of Hess's law. As mean bond enthalpies are averages, calculations using them for specific compounds will only give approximate answers. However, they are useful and quick and easy to use. Mean bond enthalpies have been calculated from Hess law cycles. They can be looked up in data books and databases. The HH bond energy is the energy required to separate the two atoms in a hydrogen molecule in the gas phase into separate gaseous atoms. So, H2 in the gaseous state is equal to 2H in the gaseous state, where the delta H is plus 436 kilojoules per mole. The CH mean bond energy is methane. In methane is 1/4 of the energy of the following process in which 4 bonds are broken. CH4 equals C plus 4H, where delta H is equal to 1664 kilojoules per mole. So the mean, or average, CH bond energy in methane is equal to 1664 divided by 4, which is 416 kilojoules per mole. You can use mean bond enthalpies to work out the enthalpy change of reaction. For example, C2H6 plus Cl2 equals C2H5Cl plus HCl. The steps are as follows. First, draw out the molecules and show all of the bonds. Formulae drawn showing all the bonds are called displaced formulae. Now imagine that all the bonds in the reactants break, leaving separate atoms. Look up the bond enthalpy for each bond and then add them all up. This will give you the total energy that must be put in to break the bonds and form separate atoms. You need to break the following bonds. 6 times CH, so you get 6 times 413 kilojoules per mole, which is equal to 2478 kilojoules per mole. Then 1 CC bond, which is 347 kilojoules per mole, and one ClCl bond, which is 243 kilojoules per mole. You add those all up, and you get 3,068 kilojoules per mole. So 368 kilojoules per mole must be put in to convert ethane and chlorine to separate hydrogen, chlorine, and carbon atoms. Next, imagine the separate atoms joined together to give the product. Add up the bond enthalpies of the bonds that must form. This will give you the total enthalpy given out by the bonds forming. You do a similar calculations, so 5 times CH, 1 times CC, 1 times CCl, and 1 times CLH. That you add them all up, and it will give you a value of 3,190 kilojoules per mole. So 3,190 kilojoules per mole is given out when you convert the separate hydrogen, chlorine, and carbon atoms to chloroethane and hydrogen chloride. The difference between the energy put in to break the bonds and the energy given out to form bonds is the approximate enthalpy change of the reaction. The difference is 3,190 minus 3,068, which is equal to 122 kilojoules per mole. And finally, work out the sign of the enthalpy change. If more energy was put in than was given out, the enthalpy change is positive. The reaction is endothermic. If more energy was given out than was put in, the enthalpy change is negative. The reaction is exothermic. In this case, more enthalpy is given out than put in, so the reaction is exothermic, and delta H is equal to minus 122 kilojoules per mole. Note that in practice, it would be impossible for the reaction to happen like this. However, Hess's law tells us that you will get the same answer whatever route you take, real or theoretical. A shortcut. You can often shorten mean bond enthalpy calculations by considering only the bonds that actually break. So that's 1 times CH, which is 430 kilojoules per mole, 1 ClCl, which is 243 kilojoules per mole. You all add that up, which is 656 kilojoules per mole, and the bonds that you need to make. So again, 1 times CCl, 1 times HCl, you add those up, and you get 778 kilojoules per mole. And the difference is 778 minus 656, which is 122 kilojoules per mole. More energy is given out than taken in, so delta H is minus 122 kilojoules per mole, just as before. This is only an approximate value. This is because the bond enthalpies are averages, whereas in compounds, any bond has a specific value for its enthalpy. You can find an accurate value for delta H by using a thermochemical cycle. That, in this case, adds up to minus 144 kilojoules per mole, compared with minus 122 kilojoules per mole calculated from bond enthalpies. This difference is typical of what might be expected using mean bond enthalpies. The answer obtained from the thermochemical cycle is the correct one because all the delta H values have been obtained from the actual compounds involved. Mean bond enthalpies calculations also allow us to calculate an approximate value for delta H for a compound that has never been made.